All right, guys, welcome back. This is going to be the final installment of the 8.8 instructional videos. Hopefully by this point you've seen the Florida problem explaining some of the ideas behind our exponential growth and decay formula. Hopefully, too, you have also seen the 8.1 or 8.8 part 1 instructional video where we dig into what the formula is, how is it different than the general exponential formula, because they're exponential growth and decay formulas. They're not really different, but they're a specific type, and looked at one example in that. And I believe you looked at the hospital example, so we won't do that one here. But what I want to do is just to shore up your understanding. I want to go through a few more examples on how to solve problems involving exponential growth and decay. So let's dig in. Suppose you go to a D3 college. This year, the college has 4,512 students enrolled. You also know the college is growing by 2.5% each year. What will the population or the student population be in 3 years? So again, when we analyze these word problems, we first need to identify what's going on. And what we see is that we're growing by 2.5% each year. And whenever you're growing by a percentage, or you are growing or you are increasing by a rate that involves multiplication. What do I mean by that? I mean, you're not increasing, say, by 100,000 or a set amount per year, but your amount is changing by a multiple. So you're doubling each year, you're tripling each year, you're being cut in half each year, you're losing half your group or your money or whatever each year, or a quarter. Or you're growing or decreasing by a percent, that's a sign that exponential growth is occurring. Linear growth is increasing or decreasing by a set amount. Exponential growth is when that amount is doubling, tripling. It's increasing or decreasing. That amount is by a multiple. Okay, so here we're growing by 2.5% each year, which is a surefire sign that we have an exponential situation. And specifically, because our starting amount of 4,512 is positive, we know this is going to be a form of exponential growth or decay. Remember, exponential growth or decay happens when your A value is positive. So our B value in this case, our B value, our rate of change, we are increasing, and we are increasing by a percent. Okay, we're increasing by a percent. When we are increasing or decreasing by a percent, when exponential growth or decay is happening, we are going to replace our B. Remember, the little thing we do is we replace our B with 1 plus or minus the percent. Okay, it's not as if what's in the parentheses is no longer B, but rather we rewrite B as 1 plus or minus the percent amount. This makes sure that we don't forget to account for the original. Again, if you want more details on that, you can watch the 8.8 part 1 instructional video. But what I'm going to do here is I am going to add, since we are growing, I'm going to do 1 plus 0.025 for my rate of change. We are increasing by 2.5% per year. The last thing we need is our exponent. And remember, x is not a specific amount of time, but the number of times our rate of change occurs. And so what do we see happening here? Well, we are increasing by 2.5% per year, and that happens for 3 years. So if we grow by 2.5% over the course of a year, that happens 3 times, our exponent will be 3. Okay? We could simplify this to be 4,512 okay? We could simplify this by writing it as 4,512 times 1.025 to the third power. And when we do that, we get y equals 4,858.9, and we'll round that up to 4,859. 4,859. Okay, and again, we will round that up to a whole value because in the context of the problem, we're talking about a population. Okay, So there will be about 4,859 students if that student population keeps growing by that same percentage for the next 3 years. The big thing I would encourage you with as you solve these problems, and you saw this in the 8.8 part 1 video, please do not just plug your percentage in for your rate of change. Make sure if you're increasing or decreasing by a certain percent, we add or subtract that percent depending on if we're growing or decaying from 1. And again, if you want to know a little bit more why that occurs, I'd encourage you to check out the 8.8 part 1 instructional video and or the Florida problem. Suppose your parents deposited $1,500 in an account when you were born that pays 6.5% interest once a year. We want to find the account balance when we graduate high school. Okay? So if what we see here again is an exponential growth situation, we are starting with a positive A amount and we're increasing over time. Our amount is increasing by a percentage. So we know it's exponential growth. We don't have linear growth here. Your initial amount, A, is going to be $1,500. Your B value, because we're increasing or decreasing by a percent, we need to throw in that 1, and we'll throw in a plus because we are increasing. Turn that percent into a decimal, and now we analyze our exponent. Okay, it's paying 6.5 interest. It's increasing by 6.5%. Your amount of money is once a year, and they put it in when you were born. And you are going to find the balance when you graduate high school. Most people graduate when they are 18. So this increase by 6.5% of the amount of money will happen 18 times if it happens once a year. Starts from the time you were born to the time you graduate high school. And when we solve this, we get $4,659.98. Again, that is rounded. Let's look at one more example. In 1990, the population of Washington, D.C. was about 604,000 people. Since then, the population is decreased by about 1.8% every 3 months. We want to know what the population will be in the year 2000. Okay? So, again, nothing new here. We're growing, decreasing by a percent, so it's exponential. But we will replace that B value with 1 plus or minus a percent. Why? Because we are increasing or decreasing by a percent. So what we need to do here is we start with our initial value, which is 604,000 people. We are decreasing, one more zero, we are decreasing by 1.8%. And now we need to plug in our exponent, but this one's a little bit trickier. The temptation is going to be to go, okay, 1990 to 2010 is going to be my exponent. 10 years go by. But what we know here is it's decreasing by 1.8% every 3 months. Now, it would be appropriate to plug in 10 to our exponent if it was decreasing by 1.8% per year, but it's not. It's decreasing by 1.8% every 3 months. Okay? So the question is, how many 3-month time periods happen in the 10-year span between 1990 and 2000? Well, 10 years go by, but per year, that decrease by 1.8% would happen 4 times, right? There are 4 3-month periods in a year, okay? So our exponent will not be 10, but rather it will be 40, since we are going to decrease by 1.8%, or in other words, we are going to retain only 98.2% of our population. And that happens every 3 months. And in that 10-year period, that means you are going to decrease by 1.8% 40 times. When we solve this, what we end up with is 292,076 people. Again, that is rounded. So if the population decreased by 1.8% every 3 months, starting in the year 1990, by the year 2000, you would only roughly have 292,000 people left. Guys, hopefully these examples help clarify how to solve some of these exponential growth and decay problems. As always, let me know if you have questions.